Ciao! Here is a conversation with Rasit Abay. Dr. Abay is an astrodynamicist and machine learning engineer. He is the founder of FuturifAI, a company whose aim is to accelerate AI adoption and to bring autonomy to use with space and Earth data. He is focused on tackling challenges associated with space situational awareness, like sensor fusion, collision avoidance, and maneuver optimization. We talk about anti-satellite tests and the space debris issue, outlining the potential of a responsible space traffic management. We discuss some challenges he participated in, like the collision avoidance challenge by ESA, and how his mixed background served him well in these scenarios. We touch on the use of reinforcement learning for space engineering problems, and how to view dynamical systems theory, like the Kolmogorov Arnold Moser theorem, using the tools of artificial intelligence. I hope you enjoy it. To support this project, please subscribe to my YouTube channel, connect with me on Twitter and LinkedIn, and support me on Patreon with a monthly membership following the links in the description. So great.
Thank you.
Thank you again for joining us. Probably it's best to start the discussion acknowledging the Russian anti-satellite tests of a few days ago to introduce basically the urgence of space situational awareness. And I will also push out there the fact that many in my, let's say, my community, my echo chamber, said in a bad way, neglect the fact that it's not obvious that national interests or partial interests are manifested in space. And so it's important that we build an infrastructure that integrates these national interests and how do you say, saves the integrity of the common ground we're playing in. And in this framework, your work emerges, I would say. So maybe you can briefly introduce yourself.
I'll start with maybe this is Russian anti-satellite one, but we know 4 other countries have done the same.
Right.
And I think irrespective of the countries, we need to be sure, space is what we need. And we need to have access to space, because how we evolve in time made us dependent on the space itself. So this is the first thing that I would say. So everyone else, on Earth, we need to come to realize we need to keep it clean for having safe access. In terms of the test itself and how it might impact how we will live or how we will do business in space, everything else that we are how we do business might change as well due to this reason. I can give you a couple of examples. What might happen? Imagine, we continue acting reckless. And then at the end, we will have a cloud of objects, lower altitudes, right? So what you need to do? You need to just increase your energy and, use the next energy area for doing all the business, right? This is how it should evolve. So then you move to the MEO. And then if it is crowded, you need to go a little bit up, right? Then each time, all the LEO is extremely, for many purposes, like the distance and everything else, it's very lucrative, right? Instead of sending all these signals longer distances. So each time we will have more difficulties, like accessing space, going beyond LEO is by itself another problem. And also using all the technologies that are a little bit higher up due to the distance might cause other troubles. And another example, maybe striking, can be right now, like we have, Starlink and all other examples. These are trying to connect all of us together on Earth, right? And also enable future, discoveries. Let's say Mars mission. Mm-hmm. So you can easily, to be honest, support these missions by those constellations. Which made things a lot easier. But if you just, make these very precious regimes, orbital regimes, by acting recklessly, so crowded, then also we are hindering ourselves to discover new things beyond, our reach. So this is what I wanted to say without any, I'm just saying this is like all of our responsibilities, irrespective of what country we belong to. But I can just give some insights about the other side, like national interests. Yeah, okay. Let's talk about a little bit about national interests, because we carry the contested environment high and high, like hypersonic weapons, and the Leo. You can just watch all these weapons. You always just carry things a bit high up, and then at the end, yeah, we start talking about national interests in space. But we need to come to realize that there is a delicate balance, and beyond the tipping point, things might get very, very challenging for all of us, and then this leads to something like nuclear race-ish area. Like you can build it, you can do everything else, but you need to be very careful not to use it. So it's the same thing. You can build it, you have the technology, but you shouldn't use it and avoid others use it, this technology. So I hope things will evolve in that direction. And as a humanity, we will optimize how we do things. And, this will hopefully increase the quality of our lives altogether, instead of, fighting with each other and coming up with local optimas. Yeah,
that's a really engineer perspective. But yeah, no, I agree definitely. When you mentioned the nuclear threat, I really see a parallel between the two, because it's like we're all in this together. So we need a framework, maybe an ethical one, a religious one. I don't know. It's not technical, but we need to find a solution.
I agree, Matteo. And this is serious. Like I don't think that it will be the end of the world. Yeah, we will move a little bit higher up, right? As I explained, and a little bit higher up, and then you carry your congestion and congestion, everything has a bit higher up, and then you have more challenges and stuff. Hopefully, once you go beyond the tipping point, once you destabilize, nature by itself tries to stabilize some point, right? It might not be optimal for us, but it will eventually stabilize in time, right? But that might lead to we will have a lot of troubles, when the nature dealing with that stuff.
Yeah, indeed. So can we start going into depth of your maybe technicalities?
Sure.
I don't know, keeping in mind this big picture, which is not technical, but yeah, how are you trying to address these challenges?
Yeah, maybe like I should start with, what I'm doing. For like, I have two directions, to be honest. Like one is business interests that I have, and the other one is like research that I conduct. And both of them, I have an overarching, approach, which is introducing learning-based approaches to challenging problems. So for my business, I'm founder and director of FuturifAI. I founded it late 2019, and from that time on, we have been building products, AI products, and also I provide expert consultancy for most of the startups. And this ranges from autonomous collision software development to from space to improving yield prediction in greenhouses.
Right.
So it might be interesting how you can do this. I think this is the nature of machine learning. So once you build a model, this overarching model, it's same. Everything else works same, right? You are learning from patterns. You put everything else in an optimization framework, and then you come up with a model that solves the problem, that works and solves your problem in real life. So this is my business interests. And for research, as you know, aside from competing here and there for space challenges, like logistics challenges, whatever I find, and when I have time, I conduct research for spaceflight dynamics, like intersection of spaceflight dynamics and the machine learning. And how I do this, what is the starting point? I look at bottlenecks, like the problems that we need something like a surrogate model to solve the problem. And I just built and try to build it various ways, either just using real data or using simulated data. So it's like a kind of mixing physical world and the data-driven world, physical model world and the data-driven model world together. And then in a way that reliably and robustly you can build those models that solves your problem. I think this is who I am and what I'm dealing with day-to-day business and also the research purposes. I don't know. Yeah, we can move to the other question.
No, I'm interested in this one.
We can,
Yeah, definitely. I'm interested in how you think about the relation between business and research, because I mean, currently I'm doing the same. I'm working as a in a consultancy for the European Space Agency, but I'm also trying to conduct research in free time. Let's call it free. But so I'm interested about how you think about those two. Is one serving the other? Are they? I don't know. How do you think about them?
I think it's all about you, how you manage, your business and your research interests, but not just research and business in general. What I do, I try to optimize my time. We are limited with time. We don't have infinite time. So if I'm dealing with a problem, let's say this is yield prediction, it's from time series information, you just try to predict what will happen next. Okay, I'm dealing with this, right? I'm just trying to come up with some solutions. If I have a research idea which is similar to this, I try to maintain it because I keep research starting with like theoretical part to the experimental part, right? I come up with a hypothesis and then I investigate it. So I use this time for research to help my business interest. And when I discover something in real life with real data, I just try to carry this experience to the research. I want to stress this, especially when it comes to data-driven research, we need to, as a community in space, in general, we need to be sure, data is critical and data is everything else. Whatever you build using whatever data is, makes your model, because it's data-driven model. If you take a look at many research, one thing striking, they are without the knowledge of the author, most of them are struggling with data leaks and overfitting problems, and which I think really important for especially young researchers to do the right way. They need to focus on the frameworks, architectures, introducing inductive bias to the problem, specific problem, versus just look at the problem as an application and use some, let's say, generated data and then, come up with an awesome 100% models, which is this never happens in real life. If you use any technique that you want, just go try. It's noisy, epistemic and aleatoric, whatever, all the noises leads to, the performances on the order of 80, 90%, maybe 95 if you spend 1.5 year or more than this, right? So this is really important. I combine what I do. If I concentrate on business, and then when I do the business, I know the capabilities of machine learning for real life. Okay?
Right. Okay.
I carry this to research. Okay, I just make everything else in a way that I make sure that any model that I build is generalizable. It's interpretable, because don't forget, this is science. We need to build something to some extent. We want it to be interpretable. It's not of course it's hard, but you can investigate under some subsection how you interpret your model, how you make sure it is generalizable beyond your training data. You are not purely overfitting. Basically, this helps me to keep this good balance, doing crazy things on research and carry it to business, and bringing sane conclusions from business to my research.
Right. Great. Yes. That sounds similar to what I think when I think about the relation between them. So there's a direction in which you use the everyday business problems to inspire you to have an idea, something like that.
Yes.
But then also you use the tools you developed from research to tackle problems that you didn't think about. So in a sense, you generalize the model you developed in research for other problems.
Absolutely. And I think it gives you confidence. It gives you trust in yourself, in the work that you do. So this is one of the things that I want to stress, like especially with data-driven methods. I think like frameworks, architectures, if it is model-centric work, these are more important. But if it is like data-centric research, then of course, like you need to focus on data, and then do descriptive analysis, and then show us how you come up with something, right?
Right. Yeah. And so, sorry, your background is aerospace engineer, because I mean you talk a lot about like a computer scientist.
Yeah, good catch. My background, that's really interesting. So I have interesting background. So I started with computer engineering.
Okay.
And then I became astrodynamicist.
Okay.
Right. So usually.
Okay. So it's the other way around.
Everything else is the other way around, right?
I did the other way around.
Yes. So like my BS, I'm computer engineer, and I did my master's in space systems engineering with the specialization of astrodynamics. So I call myself astrodynamicist, not space systems engineer, because I focus my time on orbital mechanics. So because of this, and also my PhD, combining them together. Right. So what I'm saying is, I started my life as a computer engineering mindset and formal education, and then I jump into new direction, which is like dynamics and everything else. It gives you this hyperdimensional thinking, the rotations, how you do the frame transformations and everything else in dynamics. Help me to connect this to machine learning, like the spaces, linear algebra stuff, basically advanced linear algebra stuff. And then, okay, these are the similarities, because I jump into dynamics later. It was like, baby discovering dogs are furry, right? It's, okay, this is cool. I need to understand this, why even Keplerian orbital elements can be very chaotic sometimes, like if you go into details. I'm not talking about non-gravitational forces, like gravitational forces just by itself. A lot can be done, even, the simplest thing. Like think about a three-body problem, right? Still we don't have closed form solution. So basically, I have interesting twist in my background. And on top of this, when I started my PhD, I started it a couple of times. And I have went through like courses and everything else, got my, what do they call it in some countries? Like you pass the exams, like you need to do this in some countries, but in some countries you do the research. So when I am doing all these, I always visited many departments, right? Like mechanical engineering department. I go and learn control, optimal control, whatever. If I'm interested in electronics engineering, or, I go and do like estimation, and artificial intelligence. I'm interested in computer vision department. So I pick my classes when I was doing my started PhD a couple of times. I always, pick interesting, diverse topics, and all of them, because my formal education for BSS computer science, always I connect them together, like applied mathematics, for example, like the non-convex optimization. And when you get into applied numerical optimization, oh, machine learning, everything else we put in an optimization framework, whatever it is, you have data, but the critical part is building this framework, optimization framework, and then you build a data-driven model at the end. So it helped me to learn different domains, techniques, and combine them together to understand machine learning and space, whatever, like the dynamics and everything else in the same framework, like, oh, okay, there are similarities. Let's just start with the similarities first.
Right. And so I imagine you keep doing this process. So maybe the next question could be, what's the new thing at the limit of yourself? What's the topic you're thinking about often recently?
Yeah, I think you can look at my interest in challenges. So, for example, very lately, I have participated in Last Mile Challenge, Amazon and MIT.
I saw the
Logistics Center challenge. In my life, I have never done last mile stuff. I knew the travel salesman problem, but I didn't know anything else about, like, I can't just do the math and like the techniques that they use. But then one of my friends, to be honest, in Canada, assistant professor Okan, reached out to me and said, because he knew I was competing. I was like, AI type guy. And then he said, okay, do you want to do this together? Oh, okay. But I warn you, such problems require intense domain knowledge. Okay. You can't do good by just applying, random forest or like a neural network. Yeah, you can talk about it, but no one else, you can't get something else, you'll be lagging. You need to understand the problem and build your solution specific to the problem. And then he said, this is what I'm doing professionally. He is operational, operations research scientist. So like basically logistics and stuff he was doing. So I said, okay. And he just taught me along the way, like how they do things, and I started learning it. Okay, I understand. Now I know it's combinatorial optimization, I connect it to whatever the field is. And then I did a little bit like learning, read the papers, and I asked them to do the descriptive statistics part, because it's really hard for me to understand the connection between input and the outputs. I help him very early stages, hey, we need to build a very simple model first. It's like we call a baseline, and then improve on top of this baseline. But I don't know how we will do this, because descriptive analysis will lead us to that direction. So he did a very good job, to be honest. Like, I was surprised. I told him, like, you are a very good data scientist. So, and thanks to that, we found some interesting findings and built machine learning on top of these interesting findings. So we constrain the solution space that we will search to optimize the parameters for our models. And it helped a lot. And we finished third place and got a little bit money as well. So that was really, really interesting for me to jump in new domain, new field, read 4 or 5 papers, and then compete with people literally doing this for years. At universities. That one was research challenge. So our competitors, like Lifetime, for example, the first place, like, very well known, very well respected in the field, that doing this like maybe like 30, 40 years. So that was really rewarding for me. I jump in thanks to machine learning and stuff. I build a model that can be surrogate of very, very clever people spending 30, 40 years by just learning. I did this by just learning from data. I can compete with them. I can stand next to them. So that was really, really rewarding. And I think if you ask me like one word, which experience that I'll explain to show the value and importance of AI and machine learning, it will be this one.
Mm-hmm.
You know, it's like you can solve a problem with some heuristics, but you need to spend a lot of time, right? You know, you need to know everything else. You use some heuristics with the classical methods and you solve the problem pretty good. How long does it take to solve this problem that good? Okay, like 6 months, 1 year. We don't have 1 year. Let me build something with machine learning, which can, you know, give you on the same order accuracies, but it can automatically just does this if you know how you can do this. Again, this is my principle, you know, if there's a problem, anyone else can solve this problem. Very clever people come together and build a model specifically solves this problem, right? But I don't have all the information. I don't have all the formal education to do everything else, right? AI helps me, gives me this overarching, you know, locksmith stuff. I just come and, you know, open up the locks with the power of AI and machine learning.
Yeah, nice. Yeah, and I think you're aware of the global trajectory optimization competition challenge.
Yes, I have never participated in that one. The reason is it is pure like optimization. Usually with such problems, you can do pretty good if you have good numerical like computational architecture. You can even go brute force most of the part. Of course, like, you know, these are like techniques that you can do. You can apply reinforcement learning, but the biggest problem is, and I'm giving my secret here, like the sampling, sampling efficiency, right? I always face with this. You can like machine learning, okay, something framework like reinforcement learning, something, right? That can help you build the model. Let's say for this optimization, the global trajectory optimization problem. Its name is global trajectory optimization problem. So, you know, there are techniques specifically you can use to solve that problem, like evolutionary approaches, for example. And you can connect evolutionary approaches to reinforcement learning, like applying techniques, black box approach techniques, like you know, cross entropy method, for example. You know, but then you just you need to deal with sampling efficiency problem, you know, like how many samples that you need to play per episode, you know, to update your model. Okay, so this is really big problem. You need to have very large both CPU cluster and the GPU cluster if your model is extremely complex. But for such problems, I don't believe machine learning models will be very complicated. Machine learning models I'm talking, okay? But the complexity will come how you optimize those simple machine learning models, even multiple of them, right? Many of them. So because the bottleneck is efficiency, sampling efficiency, you need to run numerical experiments, right? You need to do numerical computation. I usually stay away from such challenges because the resources, whoever has the most resources, and also, of course, I'm not just, you know, making this as simple as, oh, okay, if you have resource, you are the winner. No, I'm not saying this, but for me, I don't have such big resources. In order for me to compete with such people, I need to have very good CPU cluster, you know, and if I want to apply machine learning, maybe like GPUs, along with the CPU cluster, then, you know, I can just come up with clever ideas and compete with them. So basically, this is why I'm not participating in them. That doesn't mean that I will not. I'll take a look at it, definitely. But one of the biggest challenge for me, having the infrastructure for the specific problem. So I have my own infrastructure for building models, machine learning. I'm okay with that. But my just CPU is just best single core CPU Ryzen 9. So I need a little bit more. I don't know, like if they report their infrastructure when they bring their challenge. but it should be the case. Then maybe I'm just my prior leading me in the wrong direction. Maybe they are using just PC, and because I think
no, I've heard that in the past. I mean, that there were heavy machinery involved in trying to win this competition.
My expectation.
Yeah,
this is
but the thing is different. For example, for the spacecraft collision avoidance challenge, right?
Yes.
In which you participated.
Different. Yes, I participated and finished third place, and I introduced the best machine learning models. So I want to stress this. So the reason is for that challenge, why I can use it. The data, although looks enough, right, in terms of building pretty good models, in nature, it's never enough, to be honest, in its nature, right? Always due to the class imbalance, you don't have enough representative data. So that challenge was like that, okay? Although the data was enough, if you look, if you start immediately, but if you go in detail and do some descriptive analysis, you'll realize a very skewed and very extremely imbalanced and noisy. So immediately I just realized the nature of the problem for that one, and I built models specific to such data sets. Okay, so how I approach the problem, I said, okay, my models will be very simple. Okay, this is not a problem. Think about your features, right? How many features that you can use? They gave 100 something, 103, I think. But when I look at the features, they are the same thing mostly. Like they are the same value. Nothing will happen, right? Just get rid of them. There are dependent ones. Get rid of them. And I just at the end I had, I think, like 7 or 10 very discriminative ones. So this gave me the idea my models will be very simple. So I'll build many models. Okay, and then combine them together. Tick. And next, okay, what about the architecture? I just said I should start with investigating classical machine learning and neural networks. And then I did this. And then I realized, okay, due to the nature of the data, building a neural network model is not easy, but I needed to build a framework to solve specific problem. So for example, the class imbalance. What I have done, basically doing one-shot learning with CME's deep neural network. So I just said, okay, then I need to pick specific architecture and do oversampling and undersampling in the case for the majority class to build many models and combine them together. So basically this worked the best. And even I didn't use the raw data, I just used the statistics of that data. So I did a lot of feature engineering at the end. Although I have done all these, what I introduced was marginally better than baseline. And I think whoever realized the baseline is the best are the ones who competed at top 10, I think. All others, like, I will solve this problem with AI, jump. No, you can't do this. You need to understand the problem, the nature of the data. So they usually did poor because of that fact. And since I had background, I had advantage to build a specific solution to the specific problem. Baseline is really important. I want to stress anyone else who are using this data set. Please, if you do research and you are publishing, please just compare your model performances with the baseline. So it shouldn't have to be just the the risk value at the end. It can be maybe covariance, like the diagonal components, whatever. Please compare to your baseline. Baseline is what you have at the cutoff point, the latest information. Just compare your model performance to that one. Very simple, very easy approach to do the baseline. Why? Because really your method might solve the problem, but it might just disappear in the noise, if it makes sense. Because like, unless you do better than what exists best, I'm not interested in.
Yeah, I see. And you mentioned the fact that yours was the best machine learning model.
Yes.
But basically then the winner didn't use machine learning.
No.
Okay.
So what they have done is heuristics. And so they come up with some heuristics, some, like imagine if-else structures. But the biggest problem with that was overfitting. At the time, the organizers, I think we could submit many times. Like I can't remember, but then they stopped doing this and they decreased it to 2 per day, which was the right approach. Thanks to honest competitors, they said when we overfit, we realize training and test data distributions are different, and not that we are overfitting. So we warn you, our models, when we overfit, works for test, but not for training. So then immediately they decrease this to 2. But at the end, people already started and even like openly mentioned about this, there is distribution difference. And because you had enough time to check what type of heuristic can be done, unintentionally, most people led to overfitting, to be honest.
I see.
And also the metric for the problem was a little bit finicky, a little bit like problematic. I'm not saying, I think they did the right thing. I would do the same for the metric. But if you jump into challenge itself, if you have such specific metric, things can be manipulated easily, so which can solve the problem. So this is not about challenge. This is in general for solving the problem, if it makes sense. Yeah. So the nature of, for example, the regression part for the metric, it's useless. There was a regression part for the metric. Why would I be interested in 10 to minus 30 and 10 to minus 29, right? It's the same thing. It's very low risk. So it's not helpful for, carrying this to real life. That's why, including myself, my solution for the challenge optimized for the metric. But I knew, because I came from the field, this will not solve the problem, right? Because this is specifically optimizing the metric. Thanks. I knew this, so I also investigated the possible improvements for real life, which I'm providing help for startups for doing this right now. So like my experience lead to this, to be honest. So basically, yeah, that was the challenge. And I'm stressing again, anyone else doing research using the data, real data, use it. It's awesome. Please report your performance, model performance against the baseline. Whatever the target you have a corresponding baseline performance. Always, if it is covariance parameters, you have it, because baseline is the latest at the cutoff, whatever it is. Just use it, show, you are doing better, and then everyone else will follow you. Yeah.
Okay, great. Okay, let me ask you a question a bit technical to go in detail, but you mentioned reinforcement learning. I'm seeing recently a number of papers at conferences, also journals, to be honest, about the use of reinforcement learning for optimal control in astrodynamics.
Yes. Yes. Yes.
I approached the reinforcement learning from a different perspective, because I started doing algorithmic trading. And so I said, okay, here I see reinforcement learning to be useful. But then I went back, let's say I started seeing these reinforcement learning papers in astrodynamics. I went back reading them, and I was asking myself, why? I mean, is this a mark of decision process? Do we need to frame this? Is reinforcement learning necessary? Is it powerful? I mean, I've never used it in the context of astrodynamics, so I'm curious about this.
So like it's a good mathematical framework, right? So for making decisions at the same time. So when I look at reinforcement learning, I just see it as a framework that can help you to learn from data. You optimize your models for problems that you don't have good or explicit loss function. Okay,
Right.
so let's say algorithmic trading. I don't think that the problem is for stock market algorithmic trading with reinforcement learning. I think it is with the data itself, right? The data is very stochastic. We don't have enough observability, so the parameters are not observable enough for us to decide something. So I would say you should continue working such frameworks. It can be evolutionary. And I mentioned this, like cross entropy is the one that you can easily use and understand how it works. And it is not pure reinforcement learning, it's evolutionary approach, but you can use the same reinforcement learning framework to optimize or to build a model that solves a problem that doesn't have specific loss function. What is the loss function of your cryptocurrency? So can you come up with a loss function easily, to serve for your purpose? It's really hard, right? But what you can do, you can just say, I have a reward, which is how much money that I make, and then you can just use that reward, guide your learning in the process.
Right.
But again, I don't think that the problem is reinforcement learning, evolutionary strategies, whatnot. It is the data itself. You need to be aware such problems are extremely stochastic, right? We can't guess well ahead, and either you will go and search for different data modalities that will help you. So like this can be investigating like news, whatever you find, this might help. But unless you have good representative data that will allow you to solve the problem, it's really hard. I'm not saying this is impossible. I'm investigating, I'm checking, I'm doing myself a little bit like, stock as well. But I will not go right now at this stage, okay, I'm using this model and, it will do the job. I will never take a look at it. I do it. I just get help from models, but I always, the decision at the end is mine in terms of, buying stocks or selling it.
The agent is a person.
Yeah,
it's still a person.
So it's like imagine the complexity of the problem, right? In time we evolved to feel, to have intuition about things, and your model can only do narrow. So it's narrow intelligence. Its world is bounded with what it is provided, right? So that's why at this stage, anyone else who use, I recommend please just have a human loop, because it might be not funny if you lose a lot of money.
Yeah, indeed.
So that's it.
And so for trajectory design, the idea is the same. So basically, if you have a problem in which the loss function is not easily defined.
Yes.
Okay. And did you apply this in a specific case?
Yes, I can give you an example. For propulsion is planar phasing of multiple satellites work. So this is interesting because it might be evident to all of us, right? How to separate the space objects. Let's say you just launched and you have your cluster, and then you need to separate it in a way that you do your mission, right? Imagine like planet, okay? This is a very big problem. You need to do this fast to start, leveraging those constellations. So I had this idea at the time. I say, okay, how hard this problem is, right? If it is 2, it's easy, even without any propulsion, you can change the area to, the areas easily, like min and max. So basically you separate it. Okay, what if I increase the number of satellites, right? Even we increase to 3, things get extremely complex. Like as experts, we try to come up with some strategies. Okay, what we should do. None of them that we came up with is the same with the machine found. because machine does crazy things at some stages that doesn't make sense, but at the end, suddenly you see it's doing something crazy, and then it just finds the right combination of the area for each object, and then it suddenly stabilizes to your expectation. This was amazing. And then literally in the paper, I stress this. Sometimes problems might look like very easy, but challenge yourself as an astrodynamicist. Tell me how you will do this separation if you have 3, 4, 5, 6. It's extremely complex. Okay, so problems that might look very simple, you can say, okay, I change area to mass ratio. No, it's not happening, because you have multiple agents. When you make a decision, things get closer between some of them, and then you need to separate it again. So it becomes like a congestion, traffic congestion.
Right.
Okay, so humans, it's really really hard for us to see the long-term reward, right? Like what we will do and see in, I don't know how many steps ahead and do this thing. But reinforcement learning gives us the framework. It is for optimizing or maximizing the long-term reward. If you give the reward logically, if it guides your learning as expected, it solves the problem. It sees future within the environment. So for this problem, it was really interesting because although we provided very high fidelity propagator, even you don't have to have such high fidelity to come up with a strategy. Then you can, whatever you learn, you can fine tune.
Right.
With a very high fidelity one, just doing a couple of iterations. So in the paper, I also discussed this. Like we solved the problem with using, simpler models, and we transfer it to and check its generalizability with higher fidelity. So this is an interesting approach due to the sample inefficiency. I mentioned this to you. You need to run simulations for some episodes to take this knowledge to training your model, right? You need to do the sampling very efficiently, but numerical propagation, it's not, it's very compute intensive. You need to have many cores. So that's why how we solve this problem. In order to do a very good solution space search, we just come up with simpler numerical propagators. We train it and then transfer it and check and do a little bit fine tuning in high fidelity environment.
I see. Yeah, now it makes sense. I mean, when you were mentioning, I remember looking at the chess games played by reinforcement learning agents, and you see these moves that go outside what a professional player would do. And then you say, what's going on? And then 3 moves after that, you realize, okay, that's why he did that. Absolutely. So maybe it's the same. So the idea was in this paper to optimize basically the attitude of the spacecraft.
So coming up with strategies for each object, so each satellite, a small satellite, to change area, and we constrained it as a discrete environment, like high, low, medium.
Right. Okay.
And then each decision, which is per day decision, we got a decision out of the system, and then we apply and see what happens. So basically, we just come up with series of attitude decisions for each of them to separate equally in angle with losing minimum amount of altitude.
Right. Sure. Interesting. And what happens if you, for example, deal with a continuous control law? I mean, continuous in time. Can you still apply the same idea?
Yeah, you can do it, but then the models the methods that you apply can change. So maybe some actor critic methods will work better. Or the others will perform less. So for each problem, if it is a continuous space, for example, deep Q learning can be applied.
Right.
So for each problem if it is like continuous space, then you need to use specific problem. But this is not the point indeed, or not the most important thing. The biggest challenge is with this, and there might be a follow-up paper for this one.
Okay.
I'm not just giving hints too much, but the thing is, there's a trade-off. The way that you build the framework, okay? This one, we have one central intelligence decides for each of them, okay? This explodes your observation matrix, okay? So like you just look at the matrix and you decide, right? So there are many ways to do this. Each of them can decide by itself,
right.
Okay? So then the problem becomes, a model that is generalized over all of them, but individually doing tasks, learning individually, okay? Which is a little bit harder. You need to run longer because, now not each object needs to learn to some extent where it is in, how things are evolving, right? In this form, we provide the whole observation matrix to the system, which constrains our solution space. There might be a follow-up paper for this one. I'm working on, I hinted a lot, but yeah, interesting direction will be individually the satellites are deciding what to do and how this will affect, because this is required, to be honest, for, let's say you have 60 satellites. Like for 60 satellites, think about the combinations, and if it is continuous, and the observation space, like everything else is exploding. So the right direction, the next direction should be individually deciding what to do. So,
and then this is also pushing towards basically having spacecraft which are individually
autonomous, basically. Yeah, so for this one, we were not interested in autonomy or anything else. We just wanted to, let's say I have 10 satellites and I want to separate it. I'm a satellite operator. What's the strategy?
Right.
At first, like even reviewers, like they thought that should be easy. No, it's not easy. Like none of the strategies, and even I think one time I just said for the reviewer, like, hey, just think about it. Like, because we did it. We tried to come up with some strategies. Nothing worked. Like nothing we came up with was similar to that one, and did it faster than the machine. And then, they said, okay, thumbs up. Yeah, we agree. So that was interesting.
Nice.
For us as well. So we genuinely shared this with our reviewers. And maybe like we are approaching to the end. Do you want to just pick one that you want to discuss?
Yeah. As a first question, I'd like to discuss your master thesis, I think. The relation between KAM, Thori, and how to perform orbit prediction.
Kolmogorov Arnold Moser.
Yeah.
Yes. So this was when I was at U.S. Air Force Institute of Technology doing my master's, and I was doing this research under the supervision of William Wiesel, Dr. William Wiesel. He is a dynamical system theorist, so he is doing a lot of such research. That problem was his at the time interest, maybe still. I'm pretty sure, and trying to come up with a orbital propagator that is as fast as, or to some, of course, not exactly the same, half in terms of being fast, but on the same order, fast as analytical ones, and also accurate as numerical ones. So, like the biggest problem with propagators. If it is numerical propagator, you carry all the numerical errors, and all the artifacts, so you diverge from reality. If it is analytical, okay, you have the long-term oscillations and everything else, but then the fidelity decreases a lot, right? You can see what will happen on the order of your expectation to some time forward, but the accuracy is not that desired. So that theory was interesting one, because it just tries to build a tori So it's like, imagine like a tori. And even if you propagate the orbits in near Earth, you'll realize they look like a tori, right?
Mm-hmm.
So it just tries to build this tori or torus for the orbit. And imagine this is like a spiraling spaghetti, okay? And there are stable strings. So if you hit these strings, you will stay there for some time, okay? So using the Kolmogorov Arnold Moser theory, okay, so under small perturbations, the trajectory will be kicked in those stable orbits. You try to build this orbit first, and then do some fitting. That was my thesis, basically, fit to exactly get the parameters of chem theory for LEO orbits. Okay, so that was like, very similar like any analytical technique. You just determine the mean elements, to be honest, and then do one pace of fine tuning to exactly predict those mean elements. This is really interesting because I know in Italy, celestial mechanics people use chem theory. I know a couple of them, but this was at the time first that my supervisor, trying to apply this for artificial satellites. I was very, at the time, I was very excited to work in this. Still I am, because right now I'm really curious how I can leverage AI for these problems. And I have done once, like if you look at my two-line element estimation using machine learning, it's similar idea. Because, estimating parameters for like estimated mean elements can be compute intensive, time consuming, and especially if it is simplified general perturbations, the theory
the
itself.
SGP4.
It's SGP4. It's really it's really interesting because the algorithm not well documented and everything else. Like if you try to estimate one for you, you'll realize B star is the B star is the energy one, right? It decides how much dissipation that you have. But in estimating the TLEs, what you see is it's being used as a damping coefficient. So imagine you just predict 6 of them, 6 mean elements, and use B star to fine tune, exactly match everything else. So it goes beyond what it is for, or what it is defined for, right? When you say B star, it's for dissipation and everything else. But once you incorporate it into the estimation process, then it becomes a damper for everything else. So it just changed things in a way that it matches exactly what you expect. So it is just goes beyond, dissipating the energy part. It just changes. It makes some changes, that will allow you to fit better. So that's why most of the B star values, if you look at the official US space catalog, they are sometimes minus. Okay. So that was really interesting study as well. And also it's a part of my thesis, the PhD thesis, using machine learning for inverse problems in space domain awareness. So this is one of the inverse problem for orbital trajectory. And if you move forward to chemtori or like chemtorus theory, how can you give me, or how can you build a model that will give me a very good initial condition chem theory for LEO objects parameters, right? Because unless you have a good initial condition, the next part is fitting part. You will just go into some local minima that you are not interested in. So having a surrogate model that can give you immediately the good initial conditions for your mean elements is really important. So it not only improves the quality of your prediction, but also it speeds up the whole process. So chem theorem can be next thing that I will investigate in the future, how I can use machine learning to find these strings of orbits that are stable that might be very interesting, and like how we can discover them is a very good starting point.
Yeah, indeed. Yes. Well, okay, yeah, no, I need to read this work because I mean I just read the abstract.
Yeah, just please.
And now that I have in mind this idea of having an analytical, semi-analytical. I don't know if it's
But to be honest, it's like this one, the chem. It's semi-numerical or semi-analytical, whatever you call it.
Okay.
It's that technique. But the thing is, it's an interesting one. I think you'll like it. And I think in my thesis and in one paper, explicitly explain how you can build it. It is basically nonlinear dynamics. Like, if you go deep in, it's nonlinear dynamics and how you just treat, Foucault theory and stuff. So you will have a good like linearization and everything else of the periodic orbit. You'll go into those areas, which is really interesting as well.
Yeah. And also, as you said, trying to find a connection between these topics and machine learning.
It's amazing.
It's amazing. Yeah.
So thank you very much, Matteo.
Thank you for joining.
I hope the listeners will enjoy this.
Yeah, and for me it was a pleasure. So I hope
if you have any question, please reach out to me like anytime through LinkedIn. We can discuss if you have any question, if you have any interest, if you have a challenge idea and you want to enter a challenge. Usually I 1 to 2 people I compete because not more the merrier always. Sometimes you need to have a focus group. Thank you very much, Matteo.
It was a pleasure.
Everyone else, have a good day.
You too. Bye.